How's it going, bro? It says phew.
Okay, now that Isaac has us introduced, let's get into it. We're going to be looking at my TeleOp code. And as you can
That's a
imagine,
meme.
it's a pretty good joke. All of this code's been tested very thoroughly in my mind.
Yeah, exactly.
Okay, so let's get into the file. As you can see, the class is called main TeleOp. And
yeah, it works very well. Frick, I forgot the word. What's it called? I can attest to that. Brandon takes full responsibility if your code doesn't. All of a sudden,
Alan or Rahul
$200.
or Nabs, you know we have 3 other coders, right?
Whatever, dude. You're making the video.
Yeah. Okay. So here you can see the import statements we need for the rest of our TeleOp, right? So we also have some import statements in our hardware map, which you can see here. Yeah.
Damn, boy,
those two together, you have everything you need. So we start off by declaring a couple of variables. These are the variables for the speed of the arm and the speed of the intake. All of the code references those variables, and just like, you know, when you're setting the speed, it just like divides it or whatever. You'll see later. Right.
Damn, boy.
So we start off by declaring a new object. Shut up. We start off by declaring a new object called robot that's created. We start off by creating a new object called.
Okay.
We're starting off by creating a new object called robot, which is created using the teleop map file we made earlier. So, yeah, just sets up all the hardware. You can check out that video if you want. So next, you can see it says @override. This just, you know, forces the code to keep on running even if there's a problem.
Rip.
So yeah. So you see this method is called run op mode. This runs, as you can expect, when you run the op mode.
No way.
So we start off by initializing the hardware map. You can check the previous video to see what that does. And then we declare a bunch of different variables that we're going to be using to calculate how our robot's going to move.
It doesn't work.
It does work. You can check last 2 comps. We have videos of them, but no one wants to upload them.
Keep going.
I am. So, yeah, all of these variables, they're important, trust me. So, yeah. And then we also modify this variable to change the speed of the robot. So, when we first start running the off mode, right? So, it doesn't actually start running the off mode when you press play on the phone.
Yeah,
it starts running the off mode when you press init. It starts running the off mode when you press init on the phone, right? So, yeah. That's why you see wait for start here. That's where it starts running after you press play. You can see that we have a telemetry update here that just, it's the same thing as a print line, except for we can't use this print line because we don't actually have access to the console log. This makes text appear on the screen of the driver station, right? So it just says status shock drone going live. Yeah, it's super helpful.
It helps with debugging.
So after that, it just waits for start. So when it starts, it just says assuming direct control. Who is that?
Wait, stop. Wait, okay, hold on.
Keep going.
So when we start, it says status assuming direct control, and it'll start looping this, right? This giant loop runs the entire time the op mode is active, basically for the 2 minutes of teleop, right? So the argument of the while loop is just op mode is active. It checks if 2 minutes have passed or not, pretty much. It forces our robot to shut down when the match ends. So yeah, we start off by adjusting the speed variable, right? So it checks to see if the up on the D-pad has been pressed on either of the controllers, and if it has been, it sets the speed to 1. If down has been pressed, it sets it to 0.5. This way, our drivers are able to change the speed of the robot during the match, and yeah, we can change the speed of the robot during the match using the D-pad, and then it's an OR, so both gamepads can do it. So next is the more interesting part. We use inputs from the joysticks on the gamepad. You can see left stick Y, right stick Y, left stick X, or sorry, right stick X. Yeah.
It's actually square.
Yeah. It's, even though the thing is circular, the directions you can move the joystick in is circular, it only takes a square of that region to input into the code. Fun fact. It doesn't really matter, honestly, but fun fact.
Yes, it does.
Fine, it does. So you can see that for drive, we're using the negative value of the left stick, right? Like how much it's been moved horizontally. That's why it says Y. The reason why we're taking the negative value is because for some reason by default the controls are inverted, which is really fun. For turn, we're taking the right stick X. For strafe, we're taking the left stick X, right? So with these three variables, we're able to do math. And with math, you can be successful in life. Supposedly. That's what my teachers tell me, but they're teachers and they don't get paid much. So, yeah.
Keep
Next. Yeah, I am continue. It's still going. Don't worry. So, next, we calculate the left value and right value, right? The left value and right value are both going to be modified later on with strafe to decide whether or not the robot will strafe left and right. So, honestly, you can just remove everything that's strafe. You can remove that line, and you can remove the second half of all of these, and you'd have the code for tank drive. I mean, originally this was code for tank drive. You just heavily modified it. So, yeah, you have drive, and then you add or subtract turn depending on the side, right? And that causes the robot to turn when you move the right stick left and right. And then next, we add or subtract the strafe value based on the motor's position, right? So, yeah, you can see that all these stand for front, left, rear, right. Yeah, you add or subtract based on their position, and that allows you to blend in strafing too. So, finally, we have an acceleration curve. You can see that this multiplies it by, it squares it, but like instead of squaring it by itself, it squares it by the absolute value of itself. So if you're squaring a negative number, you still get a negative. This applies a slight acceleration curve. This way, our drivers have more control in low power zones, but gets more twitchy in high power zones. But, that's good because when you move it up most of the way, you're still probably wanting high power. When you're moving it slightly, you probably want lower power. It just helps give more controls. I mean, it's in a lot of video games, right? So, just letting the experts do their job on control schemes.
Yeah, like me.
Yeah, like Alan.
What a nerd.
I didn't even know Yunmo was here. Okay. So next we
Yunmo's
apply the speed limiter, right? So you remember the speed value from all the way up near the top of the loop where it was 1 or 0.5. Here it applies that value. Multiplying it by 1 does nothing as you can expect. Yeah. And then multiplying it by a half, makes it half as much. Oh, important thing to note, these all return a value between -1 and 1. Right? Okay, so next we have, clip the range of the power values of the motor. This way, if something broke and we get some absurd power value like 300, then, it clips it so that it's within the parameters defined by the speed value we made earlier. So that way nothing explodes. So next we set the power to the motors, right? We just take the power variables, send them to motors with robot.motor.fl.setPower or whatever. And yeah, pretty straightforward. So next we have the code for our slides, right? So, wow, you have a lot of background noise, Isaac. So, so you can see that for slide power, the math for it looks super duper complicated, but it really isn't, right? So most of the complexity, it comes from the fact that we're making it so that both the gamepad 1 and gamepad 2 can control the slides, right? You can see it says arm. That's because we used to have an arm. We just reused the code for our slides. So yeah, the left triggers make the robot go up. The right trigger makes the robot. Sorry, the left trigger makes it go up. The right trigger makes it go down. Right, and then on gamepad 2, we have this little itsy bit of code here that makes it so you can use the left stick on gamepad 2 to adjust it to. One of our drivers wanted that, so we threw it in there.
Gamepad.
Keypad.
So next, you can see we multiply it by the speed we defined for the arm, so that isn't too overpowered, right? So next, it just clips it based on arm speed, so that again, if we calculate some absurd value, like, you know, if both of our drivers press the left trigger down all the way at the same time, it will generate a value of 2, which needs to get clipped. It adjusts the slide power based on the arm, what we set for the arm speed, and then it sends that power value to the slide, right? Next, we have our code for the buttons. So you can do some really complex stuff, or on it, it's not complex stuff, but you can do more difficult stuff if you're not lazy to make the buttons toggle, but we chose not to do that. Instead, we have each button assigned a value, right? So you can see that whenever we press A, B, X, or Y on the D-pad, or sorry, not the D-pad, on the gamepad, we change the value of run intake, reverse intake, and slow intake, so that one of them are true or all of them are false, right? So Y is, you know, full stop. Each one of them forces everything else to be false and one of them to be true. Next, based on the value of these booleans, we decide what power to send to the intake. So, you know, if run intake is true, then it will make it run at intake speed. If not, it will make it run at less than that. So finally, we have the controls for the actuator. So at this point, we've already used up all of the input methods that, you know, would control the actuator, that would be able to sign, that would be able to we've used up all the input methods that would be able to provide precise control of the actuator. So we ended up using
useful buttons.
Exactly, Alan's nailed it. So instead, we're using the D-pad, right? It's pretty simple. You press up on the D-pad, it goes up. You press down on the D-pad, it goes down. And also, if you don't press anything, it'll set the power to 0. The behavior got set to break, so it'll just stay still. Oh, and also one of our drivers wanted gamepad 2 left and right to also control the actuator, so we threw that in too. Finally, we have a telemetry update to, you know, update the telemetry. We can see what values are being generated for speed, drive, turn, strafe, and slide power, right? And the intake power, but that one's not as helpful because it just returns the value of a variable we made earlier. And using this, we're able to diagnose issues with our control scheme, which is pretty handy. And updates. Diagnose. So with that, we finished the while loop. The while loop runs every robot cycle, which is around 20 milliseconds, and yeah, that's how our teleop works.
Waluigi.
Okay, who wants to say like and subscribe?
Like and subscribe.
Don't forget to smash that like button.
Yeah, smash the like button. You heard
And
it.
hit the notification bell.
Okay.
We're posting daily out here on
Maybe
the
not.
YouTube grind.
You want to post daily, Isaac? I can arrange that.